ellipsoid? Is this a blah? Is this a that? You know, what's your justification? So first thing I like to do is figure out how many variables I have appearing, right? Because that already narrows it down. I have all three appearing, right? So that rules out some things. And this is where having your book and referring to that page that I referred to is convenient because you can just start ruling things out. All right, you have all three variables squared, right? Okay. Anyone, I doubt anyone's going to remember from what we just did in class what this is, but let's see, 1/2 plus z squared over 1/3. So is that the same thing? Like 2 on top is the same as 1/2 on the bottom, and 3 on top is the same as 1/3 on the bottom. They're just moving the tables up above us. Right, so that's the same thing. So this does look like x squared over 1 squared equals y squared over what? Root of 1/2 squared. That's the same as 1/2 plus z cubed, or z squared, over the root of 1/3 squared. So we have like x squared over a squared equals y squared over b squared plus z squared over c squared. Something like that, right? And I believe that was one that we did recently, towards the end, right?
I didn't get the name for it. It's a double cone.
It's not this one, right? It's not that one, because that has a 1 in it. It's not that one, because that one has a minus in it, right? And it has a 1. Nope, that one still has a 1. Ah, here we go. Here we go. We've got all variables in here, all squared. You got 2 of them on one side with pluses between them, the other one on the other side. This is it, right? So this is classifying this. This is a what? A cone. This is a cone. And which axis does it open out? The x-axis, right? So it's not this one. It's another one of these. You get the idea here of how you do this? Well, that's this picture, but this one's solved for y. Let me.
Are you talking about the one we're doing right now?
I'm talking about this one right here. This right here.
Oh, okay.
I'm trying to match it up with one of these. Yeah, I think it's the last one here. There it is. So this is the form we have right here. All right? And that would be good enough for me. It's a cone. We're happy. Let's move on. Okay, what about this one? So you have all three variables, right? So nothing is free. How about we do this? How about we get the variable that's not squared by itself, and then move the ones that are squared over, right? And then rewrite this as x over 1/4 equals y squared over 1 squared minus z squared over what? Square root of 1/3 squared. Okay, so we got something that looks like that. And which one is that? Let's go back. What is it? Hyperbolic paraboloid. Hyperbolic paraboloid. Hyperbolic paraboloid. Oh, there we go. Let me get to the first one. I don't know if that's the first one, but no. No. There it is. Right? See that? So we've got one of the variables by itself over a number equals one of the variables squared over a number squared minus the other variable squared over a number squared. So this is our, what is it? Hyperbolic paraboloid. And that's all I'd want to know. All right? Last one. Okay. What about this one? Uh-oh. We didn't do one like this, did we? You got all three variables in there, right? Got all three variables in there. But not only do you have things that are squared, you have things that aren't squared. Right? And we haven't looked at anything like that. Have we? Let me write down something and let's see if I'm giving you a pretty big hint on what to do. Yeah, I heard it. Yes, that is correct. I think I got everything written down correctly there. Put all my x's together, all my y's together, all my z's together. And now I'm going to complete the square. So if I complete the square here, I get x squared. I take half of that, which is -1. I square it, which is 1. I add and subtract it. So I get minus 2x plus 1 minus 1. So that's what I get when I complete that square, right? Here, you have to factor -1 out first. On just these two terms, and then complete the square on the inside. So when I complete the square on the inside, what do I get?
Y squared minus 2y plus 1.
Plus 1 minus 1 again, right? So I have negative on the outside, 1, and then I have y squared minus 2y plus 1 minus 1. So that takes care of that, right? And I have to complete the square on this one, which would be z squared plus 4z, what? Plus 4 minus 4. And then plus 2 equals 0. Now I'm going to underline all the constants that are going to go together. That's going to go together. That's going to go together. That is going to go with it. I have to distribute that negative through, though, don't I? I do, yes. All right, so what do these first three terms turn into? X minus 1 squared. Okay, and then I'll have minus 1. And then what does this turn into? These three? Y minus 1 squared, but then a negative in front of it, right? So minus y minus 1 squared. Now be careful here. This -1 still had to go through to that, right? That's plus 1, and it actually kills this one off, doesn't it? Yep. I'm doing a lot of this mentally, but when that goes to here, it becomes a plus 1. It's going to kill that off. So those two are going to kill each other off. And then what's the next three terms become? X. Z. Plus 2, quantity squared. And then I still have minus 4 plus 2, right? Minus 2. And let's take it to the other side, equals 2. Okay. Everyone good up to this point? All right. If this were a plus, we'd be looking at a sphere. Because that's like the first one I ever gave you in this class. But it's not a plus. Also, the fact that we have x minus 1, y minus 1, z plus 2, it's one of these shapes we've been looking at, but what have we done to it? We've moved it, right? We've shifted it. That's all. Now, in all the formulas that we looked at before, there were no shifts. They were all centered at the origin, so to speak. Now, it makes perfect sense for us to just think about this as being one of those shapes translated around, moved over. Okay? Now, what shape is it? What shape is this? A what? So how are you getting that? I'm not disagreeing with you.
We have two positive square terms. And
Okay.
one negative square term.
One negative. And then equals 1, though, right?
Yeah, so we can divide all the terms.
Okay, good. So that, it's not this one, right? Because this had two negatives. and 1 positive, right? So this, we go back one more. I think it's here. Here we go. I'll try and make it match up. There we go. It's that one right there. We have 2 of our variables being squared, being positive, and then 1 of our variables being squared and being negative. But we all need them to be under, a number underneath, and we need to be equal to 1. So what we do is just divide everything by 2. So divide by 2 here, divide by 2, divide by 2, divide by 2. And so what we get at the end of the day is this: x minus 1 squared over root 2 squared minus y minus 1 squared over root 2 squared, and then plus z plus 2 squared over root 2 squared equals 1. So it turns out that in this particular problem, A, B, and C are all the same, right? They don't have to be, but in this case they are. You think you can handle that? Okay. We take quite a bit of time, you know, to go through all that, but that's it. I just want you to have the ability to take an equation now. So now if you see an equation that has, like, in 3-dimensional space, an equation that has x's, y's, and z's, like, we can have different types of surfaces. So we want to be able to recognize them from our little cheat sheet thing here. Use this, recognize, move on. All right, I'll turn that light back on. That made me tired. I'm sitting up here. Moving on to 10.7. What do we have, 30 minutes? Vector functions and space curves. So this is going to be a major change. We're going to be not even going to be dealing with those quadratic surfaces anymore. All right? Let me say something before I do this. For those of you who did not do exam 1, I may have made this clear already, but let me just kind of restate it. The problems on these mini exams are supposed to be challenging, so like you're not going to be able to look at any problems I did in class and it be able to like, oh yeah, he did that in class. Like that's just not going to happen. On this mini exam 2, you can almost do the whole thing. In theory, you can almost do the whole thing right now. But if you read like the questions, you have to put a lot of things together. Like, to me, the mini exam is you showing not only that you understand what we're doing here, but you really understand the broader picture of things. Like you really get it. All right? So just be prepared for that. I'm tempted to do something like one of these, but I'm not going to. Just trying to prepare you to expect to be challenged. But always try and do the homework first. You should always do the homework first. Yes?
Are we going to get our test 1 back?
I did hand it back. Yep. What's your last name? What's your last name? Here we go. There you go. Okay. All right, vector functions and space curves. We've actually looked at a vector function already. We've done one. A vector function is any function r of t. We've done an r of t in here, haven't we? It was r of t equals r naught plus tv. All right. It's any function where you have some function of t as the first component of the vector and some other function of t as your second component if you're in 2-dimensional space, or if you're in 3-dimensional space, you have 3 functions of t. Any function that looks like this is called a vector function or a vector valued function. Yeah, I think I should just show you an example first because you've already done one. If we do this, r of t equals, let's just make up a vector, 3, 2, 1, bless you, plus t times 1, 5, negative 3. That would draw what? If I ask you to draw that, what would it draw? It would draw a straight line in three-dimensional space. Now, let's put everything together. Like, let's combine it all together into one vector. What would the first component be? T plus 3 or 3 plus t. It doesn't matter how you do that, right? And then next one, 2 plus 5t or 5t plus 2. And then 1 minus 3t, right? So what we have here is a vector-valued function. It has three functions. The first function here is f of t. The second function here is g of t. And the last one here is h of t, right? So a vector-valued function is a vector function that has either two-component functions or three-component functions. In this particular example, notice that all the component functions, f, g, and h, all of them are linear functions. Linear, 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 right? That's why we draw a line. If one of these becomes like quadratic, we no longer have a line. But we have something, don't we? And so this is a specific example of a vector function, but vector functions are much more broad definition. So, vector functions. The domain of a vector function are numbers. So what I can do is maybe show you this. You know, back in college algebra or something, we would define a function. We'd say f of x equals x squared, right? And we would say to ourselves, all right, this means we're going to, do you remember this picture where you go like this and you call that little thing f? It's like a little machine. And it takes in numbers, right? It would take in a number, go through the machine, it would spit out a number, right? So numbers in, numbers out. Real numbers go in. This over here is called the domain. Real numbers come out, so the range is real numbers. Here, that's what was happening. What we're doing with vector-valued functions, r of t equals some, f of t, g of t, h of t, is we're starting out, here's r, we're starting out with a number, right? T. And what is it spitting out? Vectors, right? It's spitting out a vector. Number in, vector out. So that's what this is saying. When you're looking at vector functions, your domain are numbers, but your range, the output, are vectors in 2 or 3 dimensional space. Right? So given a vector function, we have these functions in here, f, g, and then in 3 dimensions h. Those are called the component functions. Does it make sense that we call them the component functions? I mean, when we look at vectors, this is called the x component, y component, z component. So if we have functions in there, we're going to call them the component functions. The graph of a vector value function is a curve in 2 or 3 dimensional space. As t takes on different values of the function generates vectors in the space. The graph of these vectors is not a surface. Yeah, everything's way too big here. Let me back it up. What the hell is this? Oh. So here's an example of a vector-valued function in 2-dimensional space. Here it is. It's this vector. Can you all see it here? It's 2 component functions, t squared and 1 minus t cubed. Yes?
Is this like basically a parametric equation?
Yes, you could look at these as like parametric equations. Exactly. This would be, your parameter here would be t. So it's the same thing we had. Remember when we were doing lines, we called them you could get the parametric or symmetric equations?
Yeah.
Same thing. Except this one's not drawing a line. So as I plug in values of t, right? I plug t in here. If I plug in 0 into this, I plug 0 and I get 0, 1, right? Which is the vector 0, 1, which takes me to that point. And then as I plug in different values of t, we move our vectors, and our vectors draw a curve, right? So vector valued functions are curves, not surfaces. Curves in 2 or 3 dimensional space. Here's a vector valued function in 3-dimensional space. It's the vector valued function cosine t, sine t, and then t over 5. And here's what it looks like. So as I start to draw it, see, starting here, if I plug in 0, I get the vector 1, 0, 0. But as I start to run the clock, right, as I start to run the clock, it starts to draw me all these vectors. And when you put them together, it creates this curve in 3-dimensional space, which in this case looks a lot like a spring, right? That kind of looks like a spring, yeah? I guess. Yeah. Now, can you see from the function why it did that?
Yeah, because cosine and sine is just drawing a circle.
Cosine t, sine t draws a circle. And then your z component is linear. T over 5 is just like a line. So what it's trying to do is it's trying to draw a circle. In the xy plane, it's trying to draw a circle, but then your z keeps on wanting to rise up, so it just stretches that circle out into a spiral. So if we're gonna be talking about these new functions, right? This new concept of a vector valued function, then we have to talk about all the other things we did with functions. Like take limits of functions, take derivatives of functions, integrate functions. All that we need to be able to do with the vector valued function, or else they're no use to us. So if we have a vector valued function, then, and we want to find the limit of the vector valued function, then I have great news for you. All you have to do is take the limit of each of the components. There's no other thing you have to do. In 3-dimensional space, same thing. If you want to know what happens as like t approaches a certain number, all you have to do is the limit of each one. So we'll be able to split it up. So let's do, hopefully, an example. Yeah. Let me ask you first of all, what's r of 0? So for this vector valued function, what's r of 0?
1, 0, 0. Oh, no, it'd be 1, 0, and then 1.
What happens if I plug 0 in here? Cosine of 0 is 1. We're in business there. But this, I can't plug 0 in because I'll get division by 0. It's undefined, right? There's no way around it. If I plug 0 in, this thing is undefined. Just like if I take the function f of x equals 1 over x and ask you, what's f of 0, you're going to tell me undefined, right? For the same reason, r of 0 is undefined. Yes? But what's the limit as t goes to 0 of that vector function? That's a different question, because I'm not asking you to plug 0 in now. I'm asking you to take the limit as t goes to 0. So to do that, I just need to go and take the limit as t goes to 0 of each one. And now we're going to go back to calculus. Now this one doesn't need a lot of work because we already know what happens if you just do direct substitution. Cosine of 0 is 1, nothing to do there, right? So I'm just going to put a check mark next to this one because I know that one. How about this one? What happens if I let t go to 0? The top sine of 0 is 0. Over 0, you get 0 over 0. And how do we deal with 0 over 0 when you're taking a limit? L'Hopital's rule, right? Or L'Hopital, however you learned it. or la hospital, however you want to say it, I don't care. Right? Just, if you don't know that rule, it is possible to come out of calculus and somehow have not seen that. Has anyone not seen L'Hopital? It's okay. Please let me know, though, because we need to make sure we put a huge Band-Aid on that. We're all okay? Derivative of top and bottom separately, right? So let's just do that real quick. L'Hopital on this, I would say that that's equal to, and then again, I know my students who've had me in the past know I use an L and I circle it when I use L'Hopital. A lot of textbooks put an H. I don't care. Just make sure you let me know you're doing L'Hopital's rule somehow. And then now what we're going to do is limit t goes to 0, and we do derivative of top and bottom separately. So that is cosine t over 1. And now we take the limit again, and what does that turn into? 1 over 1, which is 1. So that's going to have an answer, right? And then this one, what happens when I plug 0 in? E to the 0 is 1, 1 minus 1, 0 over 0. So again, we'll have to do L'Hopital on this. Maybe. Let's see if it works. So L'Hopital on that. Limit t goes to 0. Derivative of the top. Just e to the t. Derivative of the bottom. 1. And so that is e to the 0 is 1. 1 over 1. That's 1 again, right? So all of these are going to 1. So the answer to the limit is that you get the vector 1, 1, 1. You get the vector 1, 1, 1. So your answer is what each of these do. All right? What if one of these limits did not exist? What if one of these 3 limits did not exist? Then the whole limit of the vector function would not exist at that point. So you just say does not exist. On your mini exam that I handed out, number 4, did anyone not get this? 12? If you take a look at number 4, I give you a vector valued function. I ask you to find a limit, right? Yeah. Each of those 3 component functions requires something different to figure out the limit of. And so you'll have to go back and, open up the chest of limits that you have back and start going through and trying to remember how to do these things, right? But it'll be a good refresher for you. I gave you an easy example in class, just L'Hopital, and we were done. I don't think L'Hopital is going to get you very far on that take home. It will maybe help you on one of them, but not all of them. Let's pass around the sign-in sheet. Yeah, on those limits, I want a algebraic solution, not a computer solution, like plugging in numbers. Don't make a table and start plugging in a bunch of values. You know what I'm saying? Show me a method to do it. Okay, now continuity. We're going to blow through this quick. We have the idea of the limit with the vector function straightforward. You just do limit of each component, if you can do them. That's all you have to do. Now, in terms of continuity, it's the same definition of continuity that we had in Cal 1. So you may or may not remember the definition of continuity in Cal 1, but continuity in Cal 1 meant that if I'm looking at some point A and I ask myself, is the function continuous there? It meant, first of all, the function is defined there. It has a point. And it meant that as I approach from one side and the other side, they go to the same place. So the limit exists, and it points to the same point that the function is defined to be. So the definition in Cal 1 is limit x approaches a of the function equals the function's value at a. That's the definition of continuity in Cal 1. Here, it's the same definition. In order for a vector function to be continuous at a point A, means that as t approaches a of the vector function, it's equal to the vector function's value at a. So it's like the arrows are, the vectors are pointing towards something, right? They're trying to move to something. And then when you get there, you actually have a vector. There's a vector defined. What kind of curve is that? It's a line. Very good. Why? All three components are linear. Right? That should be a line if I draw it. What vector function would draw that line segment? I want a vector function draws the line segment that goes from that point to the other point. So I'm probably going to want to use that same one from before, right? Because it's a line segment. And I want to go from here to here. So R naught should be what? 359. And what should V be?
-5 minus 3.
Yeah, so this minus that, so -8. 2. -12, right? -3, take away 9. That should be it, right? Now we have to do one more thing. We have to restrict our t. What do I restrict t between? If I just want the segment that goes from that point to the other. 0 to 1. It's kind of weird. I don't know why I have this example here.
Can you explain why you did 0 to 1?
Because I only want the line segment. I want to be able to start at t equals 0, and that will start me out here. And then when I end at t equals 1, I'll be here. So last class I showed y'all how to do that. Like if someone gives you 2 points, you want to go from one to the other. We go from the starting point, and then we create our direction vector. And if we go from 0 to 1, we're guaranteed it's going to take us from the first point to the second. Yeah, that example just doesn't seem like it belongs there, does it? It seems kind of randomly out of place. Okay, so this one will crank it up just a little bit more. I like this example. Find the vector function and its domain representing the intersection of these two cylinders. Now, do I have a picture? Oh, I do. I have 2 cylinders. Right? I have 2 cylinders. I want you to give, no cheating. I want you to find the vector function that would draw me the intersection of those 2 cylinders. That's a lot harder than a straight line, isn't it? I mean, let's appreciate this. We want to be able to draw where those 2 cylinders hit. We want to have an R of t that draws these 2 curves, right? That's what we want. And later on in this class, we can ask how long are those curves? What's their arc length? Like what's the length if you traveled around that blue curve? What would be the length? And then if your company was welding pipes together, you would know, you then know how much weld that is, right? How much linear weld that would require. All right. Seems tough, doesn't it? Does that seem kind of tough? Let me do it this way. How about we ignore this back one, just look at this front one, all right? Just this one right here on the right-hand side. The x-axis, I believe, is coming out this way. This is the y-axis, z-axis is going up, okay? If I rotate this and we look at it straight down the y, so we're standing like way down the y-axis and we're looking in, what is it that we see? We see a circle, right? We can draw circles all day. Can't we? How can we draw circles using just t as a parameter? We did it a second ago when we drew that spiral. Cosine t, sine t. We'll always draw a circle. So I need to know, make sure to go back to this. Let me go back to this and make sure we have the equations here. So this right here, we learned just today that draws you a cylinder that opens up the z-axis, right? Because z is free, and it has a radius of 3. This is a cylinder that opens out the x-axis and has a radius of 2. So I was wrong. When I was looking at this picture, we're actually standing where? On the x-axis, looking in, right? So let me try and see if I can't get this going. I know that my vector function, to draw this, right? To draw this circle, my x is free. I mean, to draw this cylinder, my x is free. But to draw it, I could do, and you just have to, I think for this first one, you have to just see me do it. I could use 2 cosine t, 2 sine t. And this might be the first time you've ever seen this. That's why I need to make sure you're all okay with this. When we want to draw a circle using parametric equations, we use cosine t and sine t. The number we put in front is the radius of the circle we draw. I needed to draw here this circle. So I wanted the radius to be 2. Because it's y and z, I put 2 cosine t in the y as the y component and 2 sine t as the z component. Does that make sense?
Yes.
Okay. That will draw me circles all day long. All right? And my x coordinate, which means coming out at us, right? Back and forth, right now is not defined. So what I need to happen is that as I start the clock and start letting t move, right? It's going to start drawing me the circle like this. It's going to start drawing that circle for me. But what I need is as it's drawing the circle, right? As it's drawing it, if we look at it from the side, I don't want the x coordinate to stay flat, right? So now I'm drawing the circles this way, right? I want my x coordinate to kind of like, as I draw, it needs to come out a little bit, then go back in a little bit, and then come out a little bit. Does that make sense? Like, this is my x, back and forth. So how can I come up with what that is then? Like, that seems kind of awkwardly random that it's going to be like this. Maybe hyperbola, but there's something we're missing, we're not using yet. What have we not used in the problem? Mm-hmm. The other one, the other cylinder. How does the other cylinder factor into this? That curve is on that cylinder too, right? So not only do we have to be on the green cylinder, we have to be on this orangish, pinkish, whatever that looks to you, cylinder, right? So let's go back to the equations here. And what I can say here is that this right now, I'm good. I'm drawing that all day long with this, right? But I want to make sure that whatever I draw must satisfy that equation too, because it lives on both cylinders at the same time. And that's perfect because this does have x in it, right? And that's what I want to know is what's the x component. So why don't I solve this equation for x real quick? X squared equals 9 minus y squared, right? Which means x is equal to the square root of 9 minus y squared. Plus or minus, yes, thank you. Plus or minus. Right? That's what I could put here. However, y is not y. Y is actually what? 2 cosine t, right? So this is y, that's z. So if I take this and replace the y with 2 cosine t, now we have what the x coordinate needs to be. So that goes right here. And it's plus or minus. And is that a bad thing that we got plus or minus? It's a good thing because there's two separate blue curves, right? So the plus is going to draw one side of it and the minus is going to draw the other side of it. Does this make sense?
That's it?
That's it. Yeah, if you plug that in, plus or minus square root of 9 minus 4 cosine squared t, right there, and you have a computer draw that for you, you will have, well, that's what I did. That's how I had my computer draw it. Somewhere here in my code. Somewhere in my code, I had it do that.
You made all that?
Mm-hmm. The hell is it? Yeah, that was me. That was me showing the function. That's me just telling you what it is. Oh, I did that. I did mine a little different because I didn't care about. I know it could rotate it, and the axes didn't matter, so I did a little different. It looks like I did this based on a different problem, though. Yeah, x squared plus y squared is 9. That's a different problem, isn't it? Oh, no. Let me see. Hold on.
So you started off with the other equation as your
Y squared.
main.
Oh, yeah, I started with the other one. Yeah, it doesn't matter which one you use. Show intersection. Oh, here's the show intersection. There it is. Yeah, I did mine backwards. I started. Oh, well. There it is right there. Yeah, what I did is I said, okay, let me draw this. Okay? So how would I draw that? What's the radius of this one? So 3 cosine t, 3 sine t. I'm doing it in the x and the y component this time because this has x and y in it, right? And then I say, okay, what does the z need to be? Well, then I go over here, I solve this for z. And then I replaced y with this and then plug that in. That's what I used. I feel like I'm at, oh, I'm way out of time. I'm sorry.
Will they
What?
both give you the same?
They would give you the same picture. Yes. Uh-huh.
So in this case, in the one that you did in your code,
Yes.
t would not be continuous on all,
We would have different domains.
yes.
We would have different domains, which we haven't done. That was part of the question, was to find the vector function and its domain. So we haven't done the domain yet. We can come back and do that. All right?
And that's
All
where
right.
you would take the limit?
No, there's not a limit here. It's just that we do have domain restrictions. We have to be concerned about domain. It looks like for the way we did it, we're going to be fine.
So it just has to be equal to or less than 1, but greater than 0.
What does?
All the t's, because you're taking a sine or cosine, so it can't be over 1. Right. So it has to be between greater than 0, but less than or equal to 1.
Well, what we plug into sine and cosine can be anything. The input of sine and cosine can be anything. The output of sine and cosine is bounded. Right? I mean, think about your sine curve. Right? Your sine goes like, y'all can go. Your sine curve looks like that,
Yeah.
and it goes the other way. So if I say what's sine of 2, you can do it. If I say sine of 2 million, you can do it. Sine of 1, you can do it. The output of sine and cosine is bounded.
Okay.
Oh, thank you.
Those two vector equations are.
I guess they got it.
Extra one? Okay.